Hi, everybody. Thank you so much for being here today. And thank you so much to the organizers for putting on this great virtual conference and giving me the opportunity to speak about some of my recent and ongoing work. My name is Leah Jenks. I'm a postdoc at the University of Chicago, and I'm very excited to be here today to tell you all a little bit about gravitational wave probes of parity violation. So before we get in to the talk, I just want to start with the main takeaways, of which there are two. So first, I'm going to discuss a new theory-agnostic approach to parameterizing propagation effects for gravitational waves in parity violating gravity. And then I'll discuss applications of this parameterization to gravitational wave data, including the stochastic gravitational wave background, as well as the GW 170817 coincident gravitational wave electromagnetic event. And I should also say that all of the work that I'm going to be talking about in this talk is in collaboration with all of these wonderful people listed here. So given the topic of this conference, I probably don't need to say too much about parity violation, but let me quickly give a brief overview. So when I think about parity, I think about an operator P that acts on some coordinate system X and returns back negative X. So if I take my parity operator P and act it on a function f of x and return itself, then I consider that to be parity even or parity invariant. And if I get back minus f of x, then it is parity odd or parity violating. So based on our observations of the universe, it really seems like the universe quite likes parity. However, there are several key places in which the universe is actually asymmetric, and there are hints of parity violation. So the most notable example of this, of course, is the weak force, but there have also been recent hints in cosmology, in particular in CMB observations and also in large-scale structure observations, that there may be more parity than we initially anticipated, more parity violation, excuse me. So I'm going to be talking about parity violating gravity, which is a nice complementary probe to these CMB or large scale structure type observations. And when I talk about parity violating gravity, what I'm specifically referring to are modified theories of gravity, which are extensions to GR, which are parity violating. So GR, general relativity, is a parity even theory. However, it can be extended to include terms and contributions which are parity violating. So I can generally write this type of theory down with the following very generic action as a linear combination of the Einstein-Hilbert action, where here kappa is just 1 over 16 pi, r is the Ricci scalar, and then we also have some parity violating contribution, which can generically be a function of some parity violating curvature invariance, as well as a pseudoscalar field. So generally, these types of theories do additionally propagate auxiliary fields. And so this type of theory has been well studied by many people over many years. So these references that I'm listing here are by no means comprehensive, just a few examples of studies of parity violation in the gravitational sector, which can impact all of these things. So everything I'm going to say for the rest of this talk is going to be totally theory agnostic, but just to give you an illustrative example of the type of theory that I'm talking about, I'll quickly discuss Chern-Simons gravity as kind of a representative parity violating theory, and probably been the most well studied. So the Chern-Simons action is given by the Einstein-Hilbert action, kappa r, then with an addition of a Chern-Simons term. So here, this star RR is the Riemann tensor times its dual, or the Pontryagin density of the spacetime, if you like, and it's coupled to the pseudoscalar field we'll call curly theta via a coupling alpha. And it can also have a kinetic term. So when you have a correction to the action like this, the Einstein equations also get modified in the following way, where we have this contribution from CAB, we call the C tensor. And then we also have the fact that the pseudoscalar field is sourced by this parity violating invariant. And so the specific details of other types of parity violating theories arise a little bit differently, but the overall structure of these types of theories remains the same, and the overall picture is quite similar. Okay, so I want to speak specifically about parity violation in these theories in the context of gravitational waves. So in gravitational waves, there's two arenas where parity violating effects can alter things. So this is in the generation and the propagation, which are illustrated by this figure here. I will say, not to scale. But in the generation effects, these are parity violating contributions that are happening while the binary is inspiraling, merging, and ringing down at the source. So these effects arise due to the presence of this auxiliary field that's extracting energy from the binary as it's evolving. And this leads to a modified chirping rate in the gravitational wave signal. Then on the other hand, we have propagation effects, and the main effect here is birefringence, which occurs as the gravitational wave propagates from the source to us on Earth at our detectors. So what I mean by birefringence is if we consider a circularly polarized gravitational wave, so a right and a left-handed circularly polarized basis, in GR, or a parity invariant theory, we expect that the right and the left-handed polarization modes will evolve in the same way as they propagate through space-time. However, when we have parity violation, this is no longer the case, and the right and the left-handed waves right and left-handed modes rather, can propagate differently in both their amplitude and their velocity, meaning that one will have its amplitude enhanced, one will be attenuated, and the two polarization modes will move at different speeds. And these effects we call amplitude and velocity birefringence, respectively, and this is going to be the main focus of the rest of this talk. So before we get into parity violating gravity and how they propagate, how gravitational waves propagate, let's quickly review how gravitational waves propagate in GR. So if we consider a circularly polarized basis of gravitational waves on an FRW background, we can write it in terms of an amplitude A and a phase, where phi is the phase, eta is conformal time, and k is the comoving wave number. And these gravitational waves in the right and left-handed basis obey the following propagation equation, where h is the co-moving Hubble parameter. So when we have parity violating contributions, we end up with corrections to the phase. So if we have an imaginary correction to the phase, this ends up being an overall real correction to the waveform and ends up being an amplitude correction. And if we have a real correction to the phase, it ends up being an imaginary contribution to the waveform and therefore a true contribution to the phase. So now let's see how this is modified in parity violating gravity very generically. So this equation is a little bit long, but we can go through it term by term. So this first term in red marked GR is just the GR amplitude contribution that I showed on the last slide. And then next to that, we have the contribution arising from parity violating theories, which lead to parity violating amplitude birefringence effects. So this small lambda RL is just plus or minus 1. N is an odd integer. Big lambda PV is just the cutoff scale of the theory. We usually think about these things in terms of effective field theories. A is just the scale factor, and then alpha and beta are two parameters which can in principle be functions of conformal time, which parameterize the parity violation. And these two parameters are what map back to a particular theory. Then in the next term, this is the term that generally contributes to the velocity. So we have the GR contribution, and then a very similar looking term for the parity violating correction, where again, gamma and delta are these two parameters which characterize the parity violation. And I'll say here that m is an even integer. So from this propagation equation, we obtain a modification of the right and left-handed polarization modes that have these relatively long forms, but the important part to notice here is that it is h bar, which is just the GR value, times some correction, some exponential correction that is real. So this is an amplitude correction that we call delta phi A, times some exponential correction, which is imaginary, which is a velocity contribution, which we call delta phi V. And each of these have two terms. The sum is suppressed, but two terms that are proportional to this effective redshift, Zn, and effective distance, Dn. So this is what we'll use to parameterize gravitational waves in these generic types of parity violating theories. And this parameterization also maps to a wide range of theories that I'm also happy to talk about more in more detail during the in-person or synchronous session. So the last thing I want to say about this is just a comment on how this type of parameterization is derived. So there's two approaches. First, you can consider kind of a bottom-up theory approach where you take all of the parity violating theories you can think of, calculate the gravitational wave modifications, and then extrapolate backwards. One can also take kind of a top-down general approach, which is to start with a generic modification of the propagation equations, and then use dimensional analysis and expansions from GR to figure out what the non-zero terms are. And using these two methods, we actually obtain the same parameterization, so we can be very confident that it is the correct one. Okay, so now I want to turn to how we can actually use gravitational wave data and use this parameterization to learn something about parity. So we are very fortunate to be living in the era of gravitational wave astronomy, where the LIGO-Virgo-Cagra, or LVK, collaboration has ordered 100 detections from the first 3 observing runs of compact binary coalescences. And the 4th observing run is happening as we speak, so there is a lot of exciting data that is going to be coming up soon. But with the data that we already have, there are many tests of parity that we can actually do. So we can look, for example, at binary neutron stars with electromagnetic counterparts. So one of the really challenging things about measuring birefringence effects in gravitational waves is that the birefringent parameters are often very degenerate with different parameters in the waveform. And because these things are really challenging to measure, it can be hard to tell whether you have some uncertainty in, for example, your inclination of the binary or a true amplitude birefringence effect. So when we have an electromagnetic counterpart, it allows us to measure these parameters much more precisely and allow for stronger constraints. So we have a multi-messenger event, GW170817, and we're working on this. Another avenue for analysis is with the stochastic background. So I'm not going to talk about the nanograv stochastic background, which I know a lot of people have already done some interesting work in terms of PTAs and parity, but this is in terms of the astrophysical background that is expected from unresolved compact binaries. And this background does encode polarization information and is expected to be observed by LVK sometime in the 4th or 5th observing run. So we currently have a non-detection of this. Another option, of course, is to use binary black holes. There are order 70 detections, which allow one to stack constraints from many events to obtain a global strong constraint. And this has been done in these 2 really interesting papers here with the GWTC2 and 3 gravitational wave catalogs. So I'm first going to talk about these first 2 avenues. So I want to first talk a little bit about the stochastic background. So as I mentioned, we have not observed a stochastic background from compact binaries, but we can actually use this non-observation to place a totally independent gravitational wave constraint on parity violation. So the basic idea is illustrated in this figure here. So here omega is the energy density in the gravitational wave background, and this dark blue is the prediction from general relativity. So we can see that this O3 sensitivity curve is well above the GR prediction, in line with the fact that we have not observed it. However, if you have strong amplitude birefringence in your background, the amplitude of the energy density will increase eventually to a point where we should have observed it. So based on this non-observation, we can actually place an upper bound on parity violation. And this is, again, a totally independent constraint from the individual events. So some more details about how this works. So the energy density in the stochastic background can be written like this, where there's a lot that goes into this, including assumptions about cosmology, as well as the binary merger rate, as well as the waveform. So we parameterize our waveform in the following way, where we consider just an amplitude contribution, because any sort of velocity contribution to this will cancel out. And we take the lowest order contributions from the parameterization that I mentioned earlier, which now has two terms where I've relabeled alpha and beta as kappa z and kappa d, proportional, one term proportional to the redshift and one to co-moving distance. And we've just scaled by some fiducial values for numerical convenience. So our preliminary results based on up to the O3 stochastic background LIGO data is as follows, where here we have the joint posterior for the two parameters kappa z and kappa d shown in the bottom corner. And then the dotted lines are the posteriors for each of these parameters when one just takes the central cut, and then the solid lines are the marginalized, when you marginalize over the other kappa. So the assumptions that we've made here are that parity violating corrections can grow exponentially. And we've assumed for this particular plot that the merger rate follows low metallicity star formation with some evolutionary time delay. And I'm happy to talk more about some of these details as well. So this is the first constraint that actually exists on this parameter kappa z. So that is exciting. And then the constraint on kappa d is actually about an order of magnitude worse than the constraint that arises from stacking binary black holes, but is still a nice independent value and measurement to have. Okay, so I am just about out of time, so I want to say something briefly about GW 170817, which is again exciting to us because we're able to place a constraint with EM information as well as gravitational waves. So we can see that adding EM information to the amplitude birefringence measurement or constraint on the left improves the constraint about 1.5 times. And interestingly, we actually don't get a constraint on velocity birefringence from this because we have a frequency independent parameterization. This is just the lowest order correction to that velocity birefringence large sum. And because we only saw this event really with Hanford and Livingston, we aren't able to get meaningful constraints on kappa V, but we are hopeful that future detectors will be able to constrain this. Okay, so with that, I will just leave up my summary and conclusions. Thank you all so much for listening, and very happy to discuss more soon. Thank you so much.